Hello, everyone. I am happy to introduce the paper, SSP, Semi-Signed Prioritized Neural Fitting for Surface Reconstruction from Unoriented Point Cloud. Accurate surface reconstruction is a fundamental task which plays a key role in many practical applications, such as AR, VR, and so on. Concretely, given unoriented point clouds, we want to obtain the structured mesh result. We first show the main motivation of our method. First, most existing methods occasionally have difficulty in finding coarse shapes for complicated objects, leading to the production of ghost surfaces in undesired locations and large errors. In the left figure, this implies that the existing unsigned supervision may not be able to provide sufficient guidance, so as the network occasionally gets stuck at bad local minimums and generates ghost structures. A 2D synthetic example is shown in the right figure. It satisfies the unsigned distance supervision very well, but a fake surface still appears, which means using only unsigned distance supervision is insufficient. The second issue we observe is that most existing methods tend to reconstruct over smoothing surfaces in complicated regions, for example, containing details in different levels, and ignore some fine structures in this figure. To solve the above challenges, our method contains the following three components: semi-signed optimization module, loss-based region sampling, progressive positional encoding. For the ghost surface problem, we propose a simple yet effective solution by introducing an extra coarse sign supervision. The insight is that sign supervision is more informative, and we can apply sign supervision to regions that are apparently outside the target object. Specifically, we propose a novel semi-signed fitting module, which simultaneously provides coarse signed supervisions and unsigned supervisions for different regions, determined by our automatic space partitioning algorithm. With the additional signed guidance, the network can quickly fit a coarse shape to the given point cloud in the early stage, thus having higher chance of avoiding potential suboptimal local minimums within. For the lack of details, we propose a new important sampling strategy to increase the optimization efficiency and utilize progressive positional encoding to better recover the details. Specifically, we design a new loss-based region sampling strategy that tracks the losses in the full 3D space and adaptively increases the sampling density of regions with larger losses. As the semi-signed fitting module can effectively avoid bad local minimums, LRS helps the network focus on the details without suffering from severe ghost surface issues. Considering that MLP may have difficulty in fitting high-frequency signals, we explore progressive positional encoding to further improve the reconstruction. To verify the effectiveness of the proposed method, we conducted extensive experiments on the ABC subset and three types of challenging data that contain objects with fine details, varying sampling density, and noise. To evaluate the stability of our method, we compare our method in a subset of ABC, noise-free version, released by Points2Surf. This subset contains 103D CAD models with various topologies, and we use the provided sampled point clouds as input. Quantitative results of different methods are shown in table. Compared with existing fitting-based methods, our method achieves the best results on all the metrics, including F-score, CDL1, NC, and achieves comparable performance with SOTA learning-based method POCO trained on a BC dataset. As shown in figure, our method could significantly alleviate the ghost surface problem and reconstruct more accurate surfaces. In contrast, most other fitting-based methods, IGR, SAL, SOLD, and DIGS, occasionally create ghost surfaces in undesired locations, thereby severely worsening. We further conduct experiments on Thingy 10K. Similar to prior work, we use the same 5 challenging shapes with complex topology and high-level fine details. For SAP and SPS are results in table. We use the numbers reported in SAP. As shown in table, we achieve the best performance on all metrics on Thingy 10K. As shown in figure, our method could preserve more details compared with existing methods while having fewer artifacts. Although DIGS uses the Siren's neural structure for high-frequency representation, it still has difficulty in fitting the fine structures, since the points in these regions have not been adaptively sampled as many times as ours due to its uniform sampling strategy. See the abdomen of the dinosaur, shown in figure. Though SAP could successfully reconstruct an accurate surface, it occasionally creates artifacts To evaluate the robustness of our method to varying sampling density, we conduct experiments on the varying density dataset released by Pheng-Ann. As shown in table, our method performs the best on all three metrics, as shown in figure. Our method produces more complete surfaces compared with the baseline methods. Note that POCO has difficulty in obtaining the accurate surface, since the test shape sampling density is not similar to their training set shapes. To test the robustness of our method to noise, we conduct experiments on the noisy test data from Pheng-Ann. This dataset includes 57-point cloud shapes of different levels of Gaussian noise. Our method significantly outperforms others on the CDL1 and NC metrics. See table. The visual comparisons in figure also show that our method reconstructs more accurate and smooth surfaces. We conduct experiments to show the effectiveness of signed supervision, denoted as SS, and derivative supervision, denoted as DS, in table, first and second rows. For the ablation on signed supervision, we compare the result optimized by our proposed SS with the result by the existing unsigned supervision on the full space. As expected, removing either SS or DS leads to inaccurate fitting results. Furthermore, we conduct ablation on loss-based per region sampling, denoted as L or S, and positional encoding, denoted as PE. For loss-based per region sampling, we compare the result optimized by our L or S with the result optimized by the traditional Gaussian sampling, GS, strategy, which is widely used in the existing methods. As shown in table, removing L or S in our method results in a significant performance drop. Since the sampled points by GS are mostly near the surface, this may lead to inefficient sampling in the outside region for adding signed supervision. Besides, removing PE decreases the Thank you for your attention.